So in this video, we're going to conclude our derivation of the Kremser equation for describing absorption and stripping processes, starting with material balance that we began during the last class session. So let's go ahead and take a look at the material balance that we had set up. If you recall, what we did was we set up a material balance around the first n-1 stages of an absorber, where we're now describing the molar flow rates of the individual species that we're trying to absorb. So this is going to be the molar flow rate of the target species that we're trying to absorb. In the example in class, we talked about an acetone absorber, so acetone would have been the target species in that case. So we have the molar flow rate of the liquid absorbent entering and the molar flow rate of the vapor feed entering at the bottom. Remember, liquid's going to enter at the top, vapor's going to enter at the bottom. In this case, the goal of an absorber is to pull the least volatile species from the vapor into the liquid. All right, so similarly, we'll have liquid exiting at the bottom and vapor leaving at the top. Lowercase l and lowercase v refer to a per species molar flow rate. So this is the molar flow rate of one species, that target species we're trying to separate. And the subscripts refer to the stage that the flow stream is leaving. So the vapor stream leaving stage 1 gets called V sub 1. The liquid stream leaving stage n-1 gets called L sub n-1. The vapor stream leaving stage n gets called V sub n. And by convention, we then call the liquid stream entering stage 1 L sub naught. And recall, we're going to, for now, consider L sub naught equal to 0. All right, in other words, there'll be none of our species of interest in the absorbent. So we showed in class today that the liquid flow rate leaving the nth stage is related to the liquid flow rate leaving the nth-1 stage as follows. All right, so we now have a relationship between the molar flow rate for our species of interest in the liquid in the n versus n-1 stage. So we've basically figured out what the change in molar flow rate between those two stages is going to be, and we need to consider the amount leaving in the vapor, and we need to consider the absorption factor. And remember, we're going to define a different absorption factor for each stage. We're going to allow the stages to have different liquid flow rates, different vapor flow rates, and different temperatures, which will, of course, give them different K values. The n's here then refer to the stage number. We're only thinking about one species, the species of interest that we're trying to separate, so we don't need to worry about an index referring to species on these values. Okay, so what we do next is we perform another material balance exactly similar to the one we performed initially, except now instead of going over the first n-1 stages, we're going to go over the first n-2 stages. So if we explicitly draw in that n-2 stage, it would be right here. We're going to do the same dotted box that we did over the first n-1 stages, right, covering the first n-2 stages. And now into the box we have L naught, out of the box we have V1, and of course entering the n-2 stages comes little v n-1, and leaving will come little l n-2. All right, so you can do exactly the same thing that you did with this material balance that we did with the initial material balance, right? So since L naught is equal to 0, we know that V n-1 must be equal to V1 minus L n-2. Right, so this is the material balance around the red dotted box, and then we can apply the absorption factor at the n-1 stage to show that L at n-1 is equal to L at n-2 plus V1 times the absorption factor at stage n-1. All right, so you might be able to see the pattern that we're developing here. With each material balance, bringing this dotted line box up higher and higher, we're going to be developing these equations that are relationships between the liquid flow rate at one stage and the next stage, so n-1 and n. n minus 2, and n minus 1. And what we can do then is we can take this expression for the n minus 1 stage and plug it in to the expression for the nth stage. All right. And then all we're going to do is we're going to draw another data box, this time ending at the n minus 3 stage, develop a similar expression for the liquid flow rate in the n minus 3 stage, and plug it into this expression, which is already plugged into this expression. So let's take a look at what that's going to look like. So by doing material balances over the first n minus 1 stages, and then the first n minus 2 stages, we've allowed ourselves to establish the following equations. First, the molar liquid flow rate of our species of interest at stage n is equal to the liquid flow rate at stage n minus 1 plus the vapor flow rate leaving the system, that's v sub 1, times the absorption factor at the nth stage. All right, and then going over the first n minus 2 stages, we showed that L of n minus 1 is equal to L of n minus 2 plus v1 times a n minus 1. All right, so there's a pattern emerging here. We're going to do the same thing for the next n minus 2 stages. So we get L of n minus 2 at n minus 2 is equal to L at n minus 3 plus v1 times a at n minus 2. Okay, so now it's just a matter of doing this for all the stages and plugging all the equations into one another. So what that looks like, we take this Ln minus 1 term and plug it in the Ln equation, and we get an equation that looks like this. Ln is equal to Ln minus 2 plus v1 times a n minus 1 plus v1 again, all times a at n. If we rearrange this equation a little bit, we can show that L at stage n is going to be equal to L at stage n minus 2 times a n minus 1 times a n plus v1 times a n minus 1 times a n plus a n. Okay. And we're just going to wind up repeating this pattern over and over again. When we plug the L sub n minus 2 into the L sub n minus 1 equation, in other words, we're going to plug this entire equation into this Ln minus 2 term, we'll wind up getting a relationship between Ln minus 3 and Ln, and we can keep doing that over and over again. And you see that what happens for each substitution of one of these equations into the big equation, we wind up getting another a term in this first term, right? So we're always going to be substituting this L term with another one of these L terms, right? And that will add another one of these a terms to this first part of the equation, right? The second part of the equation, then, we wind up getting a v1 times some product of a's, right? So first of all, we've got our v1 on the inside here. We get that multiplied by an minus 1 and an an. The first v1 just gets multiplied by an an. With each new substitution, we're going to generate another a value, right? So that eventually, going all the way up the column, all the way to the first stage, to the liquid flow rate L sub 1, Ln is equal to L1, and then we get another a for every time we've done a substitution. All right, so notice that when we did the Ln minus 2 substitution, we got one of these a n minus 1s. When we did the n minus 1 substitution, we got an an in there. All right, so what we wind up getting then is we get Ln equals L minus 1 times a2 times A3 times all the other A's all the way to AN. And we're going to get a new A every time we do a substitution. And we've done n minus 1 substitutions to get all the way up to L1. So our first A is A2, and we multiply all the A's out through AN. Okay, then we've got this V1 term, and every time we do a substitution, we get another product of A's multiplying V1. All right, so what we'll have is V1 times, right, the first product of A's is going to be the product all the way from A2 to AN. And we're going to add to that the product of A's from A3 to AN. And we keep adding all the products of A's that we get from every substitution until we get to this last one, just the AN all by itself. Okay, so now we've got kind of an ugly equation, but an effective equation, because we now have a relationship between Ln, which, remember, is going to be the liquid, the molar liquid flow rate for our species of interest leaving the column, all right? And we've got a relationship between that, L1, which is the liquid flow rate leaving stage 1, and V1, which is the molar vapor flow rate leaving stage 1. Now this is powerful because we can substitute out L1 on the basis of equilibrium. Remember, the relationship between L1 and V1 is just the absorption factor. And in fact, we have L1 is equal to V1 A1. All right, so think about what happens to this equation now. We take this L1 term, we substitute in a V1A1 for the A1 here. Now we have a V1 times A1 times A2 times A3. So it looks just like another one of these terms, one of these V1 times the product of A terms, except it starts with an A1 and it goes all the way through the AN. So we wind up having Ln equal to a bunch of terms that look just like these terms, right? V1 times a product of ANs. So expanding everything out, we have Ln is equal to a sum of a bunch of terms that look basically like V1 times a product of A's. All right, so everything's going to be multiplied by V1. The first term is then the product of A's from A1 to AN. All right, the next term is the product of A's from A2 to AN. And we go on like this until we get to the last term, which is just AN by itself. Okay, so there's one more trick we use. We're going to do a material balance over the entire column now. All right, so take the entire column with Ln leaving at the bottom, V1 entering at the top, or sorry, V1 entering at the bottom, rather. The entire column with Ln leaving at the bottom, Vn plus 1 entering at the bottom, and then V1 leaving at the top. We've also got this L naught coming in, but remember, we've said that for the purpose of this derivation, L naught is going to be equal to 0, so we don't need to consider it. If we do the material balance over the entire column, we get that Ln will be equal to Vn plus 1 minus V1. All right? So we can plug this Ln into this equation, and we get that Vn plus 1 is minus V1 is going to be equal to V1 times this huge sum of products of A's, right? All these A's being summed and multiplied together until you have just this AN term by itself. All right, so we move this V1 over here. This V1 is not multiplied by an A, it's multiplied by a 1. So we can express it like this. We can say V at m plus 1 is equal to V1 times the product of A's, and all the way to AN, plus the next term, which is the product of A's from A2 to AN, all the way to this AN by itself term. And then because we've brought this V1 over to this side of the equation, we have a plus 1. All right, so what do we have here? We have now a relationship between Vn plus 1 and V1. Vn plus 1 is our feed flow rate. Right, so it's the molar flow rate of the species of interest in the feed. V1 is the product flow rate. Again, molar flow rate of the species of interest in the product. So this equation is actually a design equation. What this equation gives us is a relationship between the feed and the product based on the absorption factors at each stage. We can simplify this further by applying what's called a group method. What we're going to do first is define what's called the recovery fraction. So the recovery fraction is defined as the ratio between V1 and Vn plus 1. And the symbol we'll use is lowercase phi, and because we're talking about an absorber, subscript A, recovery fraction for an absorber. All right, so this is called the recovery fraction. And what it represents is the fraction of our species of interest leaving as a product in terms of the species of interest entering as a feed. So since our goal is to separate separate the species of interest from the vapor feed so that it does not come out in the product, the smaller the recovery fraction, the better. Right? You want a small recovery fraction. A small recovery fraction means that you won't have much of your species of interest leaving in the feed. That is, your species of interest has been successfully transferred out of the vapor phase and into the liquid phase, just like you want for an absorber. All right, so based on the equation that we just developed, right, so the recovery fraction then, VA, is equal to V1 over Vn plus 1. And the equation we just developed told us that this ratio, V1 over Vn plus 1, is this huge sum of products of A's, right? So we're going from, in the first term, the product of A1 all the way through AN, plus next term is going to be the product of A2 through AN. Keep having a bunch of terms like this added together until you get to the second last term, which is just AN by itself. And then the last term is 1. All right, so if we have the recovery fraction, we can calculate basically what's in the product based on what's in the feed. All right, this is useful for engineering design. This tells us what we need to know about our designed absorber system. But this equation as it is incredibly unwieldy. I mean, you've got to calculate a separate absorption factor for each stage, and it's impractical. So in practice, what's done is what's called a group method, where instead of explicitly calculating the absorption factor for each stage, you assume that there's some effective absorption factor. So you say that A sub B is your effective absorption factor. And the effective absorption factor is basically defined such that when you replace all of these A sub i's with an AE, you get the right answer, right? So it's effective means exactly that. It's effective at giving you the right answer. All right, so if we do this, we get phi of A is equal to 1 over, all right, so how many AEs are we going to have here? We're going to have n AEs. So we have A e to the n plus, okay, in the next term, we're going to be going from A2 to AN, so we'll have n minus 1 AEs. These are all multiplied together. So on and so forth until we get to plus AE plus 1. All right, so we've replaced all the A sub i's with this effective absorption factor, AE. We can show pretty simply that phi A is then going to be equal to AE minus 1 all over AE to the n plus 1 minus 1. This equation is called the Kremser equation. And its power is that it gives you this absorption factor, which allows you to calculate the flow rate of the product once you have the flow rate of the feed. All right. Remember, the smaller the recovery fraction, the better. You want a small recovery fraction. A small recovery fraction corresponds to a good separation. One thing that this allows you to do, even if you know nothing about what you need to calculate AE, if you have a working system and you know how it performs, you know what its recovery fraction is, you can calculate what the absorption factor must be for that system based on the Kremser equation. And then you can design what a change in the number of stages would do to that system. You can also design, based on what you know contributes to the absorption factor, liquid flow rate, vapor flow rate, and K value, based on how changing those liquid flow rate, vapor flow rate, and K value will change the quality of your separation. You can use exactly the same approach to describe the performance of a stripper. All right, so for stripping, recall, now we have our liquid product entering at the top with liquid flow rate L. And now here's the trick. Strippers are labeled in the opposite direction as absorbers. So stage 1 is at the bottom, and at the top you have stage N, stage N minus 1, etc. All right, so the liquid product, or the liquid feed rather, entering the stripper is going to have flow rate Ln plus 1. All right, and then the exiting liquid, the liquid product, will have flow rate L1. All right, so here we have feed, and we have product. All right, and then the stripping agent entering at the bottom here has flow rate V naught, and again we're going to assume that this is equal to 0. In other words, that the hot gas that we're entering into the system to remove our species of interest contains none of that species of interest when it enters. And exiting, we're going to have a flow rate V sub m. All right, so we can use exactly the same method that we used with the absorber to show that for the stripper, L1 is going to be equal to L n plus 1 times what we'll call phi sub s, the recovery fraction, now instead of for an absorber, for a stripper, so we put a subscript s on it. So again, this is the recovery fraction. Okay, and the recovery fraction, according to Kremser's group method, is related to what's called the stripping factor, in this case the effective stripping factor, S sub E, minus 1 over S sub E to the n plus 1 minus 1. So exactly the same Kremser's equation, except now we have S instead of A, and S is simply defined as the reciprocal of A. Okay, so S is equal to 1 over A. So it's going to be equal to K value times vapor flow rate all over L. All right, so just as having a large value of A favored absorption, having a large value of S will favor stripping. So if we have a large K value, we have a species that prefers to go into the gas phase, which is what we want if we want to pull that species out of the liquid and into the gas. Okay, so I talked about these being effective stripping factors and absorption factors when we use the Kremser group method. In a lot of cases, if you have a system where V, L, and K are all relatively constant over the column, over the stripper or absorber, then you can actually calculate an S or an A based on the appropriate equations, right? So again, S equals KV over L, and A equals L over KV. And then you can use these in the Kremser's equation together with the number of stages in the separation in order to calculate your recovery fraction. And remember, the smaller the recovery fraction, the better, because you want the amount of species of interest leaving in the amount of species of interest leaving in the product to be small compared to what enters in the feed.